So this is a continuation of our discussion on electron configuration. Suppose you can't memorize how the orbitals are arranged according to increasing energy, then no worries. All you need to do is just look at your periodic table, which is a very handy and useful tool. Okay. Take note that the periodic table are arranged in such a way that it also reflects some information about how electrons are configured or arranged. So the rows here represent the main energy levels or the principal quantum number, but I'd like you to take note that whenever you reach the violet block here, which is our D block, then we just subtract 1 from the energy level. So N minus 1. All right. So after calcium, if you have to go through the D block, okay, for example, the last term for the electron configuration of calcium is 4s2. So if after 4s2, you still need to go to, for example, a gallium here, and then you need to go through the D block. So you do not say 4d10, okay? You do not count 4d10, but you say 3d10, okay? Because n minus 1 here. If you try to go back to the arrangement the of the atomic orbitals, what actually comes after 4s is 3d, okay? Before you could proceed to 4p. So that means there is some changes in the pattern as we go over 4s and beyond. In the same manner, okay, once you reach the F block, okay, so right after lanthanum, okay, lanthanum and actinium are still members of the D block, okay, and then these are now your F block or F transition elements. So whenever you have finished lanthanum already, just remember that when you reach the F block, then N, okay, you might subtract the energy level N minus 2, right? So n minus 2. So for example, you start with 6s2, and then you go through lanthanum, which is 5d something. And then after that one, you need to go through the F block. So n minus 2, that becomes 4f blank, or 4f2, 4f3, so on. All right. Okay, but we will concern ourselves mostly on the representative elements, okay, and not so much on the transition just for now, because there are a lot of things going on with the transition metals, okay, in terms of their electron configuration. So let's start. Let's start with a few examples first. Uh, let's say we want fluorine, okay. Make it a little bit smaller there. So let's say I want to give the electron configuration of fluorine. Okay, this is a good practice to write the atomic number, okay, uh, before your element so that you will be guided. Okay, so if fluorine is neutral, it has 9 protons and also 9 electrons. The problem is, how do we distribute those 9 electrons according to its into its atomic orbitals. Okay, so in using the periodic table, so we can just start here. So this is 1s, then we count the number of cells present. Remember that the blue partition is your S block. So 1s, and then we count how many cells it has to go through first before it reaches fluorine. So imagine helium is here. So it now travels 1s2, okay? After the 1s2, then we have 2s2, okay? After 2s2, okay, again from left to right, you have the 2p something, and then we just count how many cells it takes before we could reach fluorine. 1, 2, 3, 4, 5. So 2p and then 5. How do we know that our electron configuration is correct? Okay, we just look at the number of electrons present in each in each orbital, and we make sure that their sum is the same with the atomic number here. So this is 2 plus 2 is 5. Then that's 2 plus 2 plus 5 is equal to 9. So more or less, so they're the same. Therefore, we got the correct electron configuration for fluorine. All right. Let's take another example. How about, and then I think it will be a little bit longer now, but let's have gallium. Now, gallium has an atomic number of 31. That's Ga. So we use the periodic table method. So we start with 1s2. Okay. It has traveled that 1s and then block. And then after that one, 2s2. After 2s2, so from left to right, this is 2p. And how many cells are there? 1, 2, 3, 4, 5, 6. So 2p6. After 2p6, we have 3s, right? 3s2. 3s2. And then after 3s2, you go here. This is 3p6 still, because you have to travel all the way to the 3p block. After the 3p6, then you get 4s2. After having 4s2, this time we cross the D block. Okay, remember after the 4s2, after calcium, then N minus 1, so that gives us 3D. And then how many cells are there that you have to cross? There are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. Okay, so 3D10. After 3D10, at last we have reached gallium. Okay, so that is, we go back to 4, right? 4p1. Alright, so 1s2, the handwriting is quite messy. Trust me, this is not my handwriting when writing on a whiteboard, but yeah, it's quite difficult. Anyway, this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. Sir, that's quite too long. Is there any way to make it a little bit shorter? Okay, yes, there is. But first, you just have to make sure that the number of electrons add up to the atomic number. So this is 2 plus 2 plus 6, that's 10. This is 12 plus 6. 12 plus 6 is 18, 20, 30 plus 1, 31. Okay, we're doing well. That's 31. So how do we make this shorter? This time, we are going to use the condensed. Okay, the condensed electron configuration, which uses the noble gas before, okay, right before the element. So let's just write it here first, 31 gallium, and then we enclose that noble gas with with a bracket. Okay, what's the noble gas right before gallium? It is argon, right? So 18 argon, that's 18 1/8 AR, and then close. And then after that one, we start counting from the element after argon already. So this is 4s2, and then after that one, 3d10, After 3D, 10 is our 4, excuse me, 4p1. Okay? And how do we check whether we're correct? So we just look at the atomic number of the noble gas. That's 18 plus 2, 20, plus 10, 30, plus 1, 31. All right? So that's how you do condensed electron configuration. Another example, okay? Maybe one last example. Uh, it might take a quite a long ride, but sige, let us have iodine, I. So let us just give the condensed electron configuration of iodine. This is 53. Okay? So again, we look at the noble gas right before iodine. And as for this case, this is krypton, right? So 36 krypton, Kr, 3, 6, Kr, parenthesis, or bracket rather, and then we continue with the next. This is 5s, 2. After 5s2 is again 4d 10. After 4d10 is what? Going back to 5p. 5p. Then what number of the cell? 1, 2, 3, 4, 5. 5p 5. Alright? So 36 Kr, 5s2, 4d10, 5p5. Now, if you have ions, you just have to subtract the number of electrons. For example, if it's subtract or add the number of electrons. So, for example, if this fluorine becomes F minus, F minus now, remember that the sign negative here denotes that there is an added electron. Okay, it has been ionized. It has an added negative charge. So there must be an added electron. So instead of 9 now, okay, the atomic number is still 9, but this time the number of electrons isn't 9 anymore. It must be 10. So what happens to that one electron? Then where do we place it? So we just have to follow the order 1s2, 2s2, and then 2p. So if we add one more electron, remember that the p block, the p sublevel can accommodate a maximum of 6. So pwede pa. So this is 2p, 6. Okay? So if you've noticed, the fluorine ion here has 10 electrons and it will follow the electron configuration of neon. Okay, it will have the same electron configuration of neon. So if that happens, we say that fluorine ion, F minus, is isoelectronic. Okay, the same number of electrons. Isoelectronic with neon. Okay, meaning it has followed the configuration of neon. Isoelectronic. Okay, and that will reach now isoelectronic series, especially for example if Na here, Na loses its one valence electron, it loses one electron, it will also follow 10 electrons or follow the configuration of neon. So therefore, F minus Ne and Na, sodium rather, are called isoelectronic series. Okay, isoelectronic series. All right. So much for that. I'll be leaving you with an activity later. The main skills are to draw the orbital diagram, to give the electron configuration, and to give the condensed electron configuration of atoms. And I hope that you can also do the reverse process, wherein, for example, you are given the electron configuration and you need to find what element that is. Okay? So, for example, for P1, 4P1 is the last term. Just look at directly the main energy level for P, and then which is at the first cell for P1, so it's gallium. Okay, so that's just the reverse. All right, so that's it for electron configuration, orbital diagram, condensed electron configuration, isoelectronic species, and isoelectronic series. So let's have a few exercises after this lecture. And thank you very much for your attention, and you stay safe.